Thank you. Yes, I will. I've already heard the name coming up a number of times. So I will introduce the mission. I will not introduce the context, which was already sketched by Hugo and Richard and yourself. So the full name is actually, well, anthropogenic greenhouse gas monitoring with Copernicus CO2 monitoring mission. And I'm the mission scientist. I'm responsible for the mission requirements. Obviously, this is a mission that is not done alone. So there's a whole project team. There's the support from the European Commission in Brussels with Hugo Sunker and Eric. And there's an advisory group that is helping us to support this. There are also institutes. We're not doing this alone. So there's also EUMETSAT like Sentinel-3, and there's ESA, but that's more for the services to implement this. So I think we are suffering a little bit from the majority of other aspects in the services. So we get really the full scale of all the requirements. And initially, actually, Sentinel, this CO2 was actually targeted to be part of the Sentinel-4 and 5, well, actually the Sentinel-5 mission. But it turned out that it really is a mission on its own. So if we look at the overall support capacity that Richard sketched, if you look at the system requirements that are flowing down to the observations, it's the red one. So it's the detection of emitting hotspots. We're trying to monitor these hotspots over time. And then on a little bit larger spatial scale, we're also trying to look at the changes over local reduction targets, like nationally determined contributions from countries. And then on a much longer time scale, we're looking at the global stock take, which are done every 5 years. And in terms of what it means for satellite observations, it has various, actually sometimes contrasting requirements. So you really need high precision data and high spatial resolution for the local scale aspects. But if you need to go to the larger scale aspects, you really cannot sustain any drift in the data or biases, and you really need intercalibrated satellites. You need to be able to very well separate biogenic effects from anthropogenic effects. And there have been a number of reports to describe the overall system, and I think it's really nice that we built it up from the beginning in a system context. So now I'm really jumping to what it means for satellite mission. So we are measuring CO2, but we basically choose a band to measure this around the 1.6 micron, where there's also methane. Part of it's because of the trick that we can do what's called the proxy method. So you can actually derive a CO2 product with using methane as a stable background. But as a consequence, we actually measure methane as well. If you look at the plot below, that is simulated data over Germany, you can see the city of Berlin, very faint. You can see power plants a bit to the east of this simulated swath width. If you would look at this with NO2, NO2 is also co-released in high temperature combustion processes. And it has a very low value in the background because it's not, it's chemically active, unlike CO2, which is very stable and actually causing part of the climate change problems. So we're actually measuring NO2, and in order to know where the plumes are and better average in the regions where we are interested in. And this really helps us to improve the data quality and quantity. We have several viewing modes because we would also like to measure both water and snow, which are known to be very dark in the shortwave infrared. So if we now look at the more observational requirements, very, very stringent requirements for any mission, but especially for the very difficult CO2 observations. So we need all the different bands that we're having. So we have 3 bands for the CO2 and methane, and then 1 in the visible for the NO2. They need to be co-registered within 95%. And it's amazing that the current concept that we're having is actually reaching beyond this value. We also would like to know very well where we're looking, so we can actually locate it with the targets on ground and other aspects. So it's the traditional way of push-broom imager, like it's done for Sentinel-5 precursor and for the Sentinel-5 that are upcoming. Then another aspect that is very important for, well, especially anthropogenic greenhouse gas emission, is you need to know very well what the light path is. So if you look at the data that I showed you before, the requirements, we're looking at a below a percent, actually below 0.5% precision. And the bias needs to be even way below that. So if you look at what the light path is through the atmosphere and what then causes where the CO2 is, a very small change in the light path, for example, due to aerosol or clouds, will change this error budget and completely upset it. So current satellite missions are filtering out data with too high aerosol optical depth. And those are actually the regions of interest. So if you look at the MODIS aerosol depth on the bottom right, you can see that over India and China, there's consistent high levels of aerosol, which would prevent proper data. And you see this in current satellite missions that are filtering out data over these regions. So we will actually include what we call a multi-angle perimeter. And if you simulate the data, you see that on the bottom left, if you use it or don't use it, it makes a huge difference. So we were actually able to have good data up to high aerosol loads. And we currently set it to 0.5, but it might be that we get better data beyond that. And we would also like to avoid to use data where there are clouds. So we also have a cloud imaging. We're implementing this with a multi-viewing angle colorimeter, looking at polarization in these 7 bands that you see there on the left. And also very, very demanding degree of linear polarization. So it's the error in it that is very high, and also very high spatial resolution. On top, as I said, we have a cloud imager for the lower clouds. That is the first band. Another band that's actually, if you've paid attention to the different instruments, we have this band near 753 in all the instruments. So that's basically giving us an overview of co-registration. So it allows us to intercalibrate and to co-register. And the third band is is actually what we call a cirrus band. It's a saturated water vapor band. And if there's any light scattering, it must be from near the tropopause, where there is probably cloud and scattering the light back to space. So if we now look at the space segment, so we're looking at a close to noon orbit in a very familiar altitude, around 700 kilometers. And we would like to get multiple satellites to get improved coverage. So you've heard in Sentinel 4 and 5, there will be more units, but they will be sequential. We're actually looking for a constellation. And the design lifetime, like most of the satellites in Copernicus, is 7.5 years, potentially extendable to 12 years. So the fuel needs to sustain this. And these are our impressions of the satellite. Oops, that goes too quick. The payload, like I said, it's a push-broom imaging, but yeah, you can see on the top left, actually things are taking shape. The design and actually the ceramic bench that is very stable and provides us all of the 4 bands into one instrument, so including NO2. We actually have what is called, might see it, it's called 2DSH. It means a two-dimensional slit homogenizer. It's basically a fiber. And this allows us to do this very high co-registration in spatial domain, and also to homogenize scenes on Earth that are otherwise heterogeneous and disturbs the observations. Multi-angle perimeter, also very novel concept, where we actually, on top of the detector, apply filters and polarizers. And in this way, you get this all the 7 bands very well co-registered, including all the angles that we need. And a cloud imager based on the ProbaV concept of Belgium. So science support studies, I think I'm not sure how I'm doing with time, but we are looking into how to improve the coverage over snow-covered regions. Obviously, there is a large area where there's snow cover. Snow is pretty black in the shortwave infrared. But if we look in what we call the glint modes, so you're looking actually like over water. If you look at the the polarized, well, the bright spot over the water, you can get better radiance levels. And the same applies over snow. So we really try to reach the optimum places to look at, and the optimal configuration of the satellite to have good coverage. Another activity that we're doing, because I told you that we have this multi-angle polarimeter on board, is actually quite new to this kind of satellite missions, and we really wanted to be convinced that we are doing the right thing. So we added, we have another study that's ongoing with the University of Leicester, and they're basically confirming the results that we already obtained, showing that we can get the precision and the bias in the range that we want to have them. If we make use of a retrieval that uses both the data from this multi-angle polarimeter and from the CO2 measuring instrument. Some other upcoming studies. Well, we always need support for the CO2M project. There will be challenges to requirements, and we need to understand how big the impact is and if we can live with that. And what we call the mission operational concept study. It's actually looking in how shall we interleave to be in what we call glide mode or in the nadir mode, which is basically means you're looking straight down. And there's some trade-offs to be made there, and we really need to understand the details from it. We had the implementation status. So we had preparatory activities for quite some time. The implementation started 2 years ago. Right now, we are still on schedule. We completed the satellite preliminary design review. And we are ongoing with the payload PDR, preliminary design review. We signed the contract already to continue into the next phase. So I wrote here is at the Living Planet Symposium, but we are here obviously in the Commons General Assembly. So we have finances for the first and second satellite, and they will have their what we call flight acceptance review. It allows to have a launch in the end of 2025, and hopefully we're going to get also a third satellite. The data processing, like some other Copernicus missions, will be done by EUMETSAT, very well capable of processing large amounts of data. And here I give you some impression of the amount of data that we will get down. Of a single satellite in a single orbit. It's really incredible. And just to give you an impression of how one satellite looks like and how then in different colors they will come up, how 3 satellites would look like. It's 250 kilometers swath, and you will slowly start mapping the world and allowing both the regional scale analysis as well as the plume analysis, so more local scale and city scale. And this is just to sketch you the enormous consortium that is helping us to implement this on the industry side. And with that, I would like to thank you.
Yashka, thank you for the presentation. It's really incredible to see the progress in such a short time frame. So between the start of implementation to launch possibly in N25, it's quite incredible, and it's great to see that it's on track. There is more and more information. Do we have some questions? Yes, Simon. Just wait for the microphone.
Yes, thank you, Yashka. A very simple one. Is there any prospect to retrieve N2O as well later on?
No, unfortunately not. N2O from space is very demanding. I think it can be done maybe in the more infrared, thermal infrared, but to the level that you would need it for looking at anthropogenic effects, this is really difficult, if not impossible.